This problem comes from David Roylance's page on pressure vessels, which you can find at the above link. We have a compound cylinder which has an inner cylinder with radius R1, thickness T1, and elastic modulus E1. And there is an outer cylinder fitting snugly around the inner one that has properties R2, T2, and E2. And the question is, what is the hoop stress in the outer cylinder? So to start this problem, let's draw what the compound cylinder actually looks like. So for that, we have an inner cylinder with radius R1 and a thickness T1. We also have the outer cylinder, which we'll say has radius R2 with thickness T2. And this problem is kind of a, how do you say it, a flashback to being able to write out the three pillars that we haven't discussed recently in the course, but the three pillars being equilibrium and geometric compatibility and our constitutive relationships. So this technique comes from what I guess I was kind of taught when I took mechanics, and is something that Crandall Dawn Lardner would espouse. So let's kind of break this problem into these three categories and see if we can make heads or tails of what is happening. First, with geometric compatibility, what we're going to say is that the change in the radius R1 is going to be about the same as the change in the radius of R2. These annular components are very thin, they have small thicknesses, and so you can kind of see that if the two rings have to be, well, compound with each other and they have to be snug and they have to be going with each other, we can see that, okay, if R1 moves a little bit, then R2 is going to move that same amount. Okay, so R1 is equal to R2. We also did example 15.3 in class, and so you can take a look at those notes if you like. That described the constitutive relationship for the change in radius versus the pressure and the elastic modulus and the original radius and the thickness, right? This is a constitutive relationship because it's telling us something about how the displacement or how the deformation is related to the loads that we might have in the system and a material property, namely the elastic modulus. So you can take a look back at this if you like, in the notes or in our session that we had. Next, let's go over to equilibrium. So with equilibrium, and this is kind of a general expression, right? So we're saying that delta R is, could be R1, it could be delta R2, okay? And like this could be a P on the inside of one of these cylinders. The same thing with the radius, the elastic modulus, and the T, right? Because we have different properties for the two cylinders. So let's go about and kind of draw just a portion of what we have here. We have one cylinder on the inside, one cylinder on the outside. We have pressure on the inside. We're considering this to be a gauge pressure, okay, inside the inner cylinder. And probably a good idea to say that gauge pressure is essentially the difference in pressure between what's happening on the innermost, okay, on the inside cylinder and out here, okay? So another way to think about this is the pressure inside, it's kind of absolute, and we'll just say this is like 0 out here, okay? If we now draw the outer ring, okay, so we're taking this green part out here, and we just draw it again. What we see is there's going to be some pressure that's causing the outer ring to be in tension, okay? So let's call that PC, P sub C, all right? So, if there were no inner ring here, okay, this between the green and the black, then, this PC would just be acting on this outer ring. Well, there is an inner ring, and if we draw the inner ring, we can say, okay, there's a pressure on the inside, which is the P, right? Which, relative to out here, we're going to say is something significant and is gauge pressure. But what's acting on this side of the inner ring? Well, normally we try to be very careful in equilibrium and keep it to forces. Uh, and we can kind of extract that here as well. If we said the radius is very large and these are kind of just like plates that have some area to them, we can see that the pressure that is acting on this cylinder, the outer one here, is got to be the same as the force, right, on that plate, better said, and the force associated with this PC acting on here has to be the same acting on kind of that plate. And so we do have equilibrium. This is an equilibrium condition. This is exciting, right? Because now we can kind of decouple these two rings in terms of what might be happening to their change in radii, and we know their change in radii are the same. The last bit of equilibrium that I'll put out here is that we are being asked to calculate the hoop stress in the outer cylinder. So now that I've got a pressure and I've got, let's say, a radius and a thickness for this outer ring or outer cylinder, I can just use the equation that we've talked about before that relates the internal pressure, the radius, and the thickness for a thin-walled cylinder, and for the hoop stress to the hoop stress. Okay, like we see here. Well, let's start plugging some things in to each other. So one is that we can say, all right, delta R1, all right, I can use this constitutive relationship right here. So delta R1 is really kind of this delta P1 R1 squared E1 T1. All right. Now, what is this delta P1? This is maybe, I don't know if it's the trickiest part of the problem, but it could be. It's maybe not intuitive until you've broken the outer ring and the inner ring or decoupled them, even though they're compound. What you see here is that this delta P1 is really going to be this inner P minus this PC out here, right? This is just the definition of a gauge pressure, and we could have put P1 here if we wanted, okay? But this is the gauge pressure for this inner ring, and it's not the gauge pressure between this P and the outside. It's just the difference of pressure acting on this ring. So it's going to be P minus PC. And once again, we're just copying that part of the relationship. For delta R2, we can write that this is the gauge pressure, PC, and we simply substitute as is appropriate. We now use our geometric compatibility, put these two equal to each other, and we have the following. P minus PC, right, over here, times R1 squared over E1 T1 is going to be equal to PCR2 squared over E2 T2. What do we need to solve this problem? We need to figure out, well, the hoop stress, but what we don't know right now is PC. We do know P, and we know all the other properties. So what we need to do is we need to solve for PC and then plug it back into this equation over here and figure out what the hoop stress is in the outer cylinder. So let's go ahead and break things down, do a little manipulation here, right? We can move this PC over to the right side, but it's got an E1 T1 in the denominator for it and an R1 squared. We can then essentially just divide both sides by this quantity in the parentheses, and we get that PC is equal to PR1 squared all over a big E1T1 times quantity R1 squared over E1T1 plus R2 squared over E2T, and then ending of that quantity in the denominator. Okay, so I suggest you use your thumbs very carefully with a calculator, or you use Python or Colab or MATLAB, whatever it is, but to calculate this out. Because you can plug in all these properties here, calculate the PC, and then plug in the PC right here. And just, I think uh, the Canvas page is asking for the final answer in megapascals. So just remember that 10 to the 6 pascals is equal to 1 megapascal. So if you're keeping your units all in pascals, in the end, you're going to want to multiply by 10 to the minus 6. All right. Thank you. I hope you found this example useful.